Hello, everyone. Thanks for joining another session of the Quantum Talent Showcase, which is a bi-monthly series of presentations from quantum students and postdoc researchers at top universities. It is organized by QED-C's Workforce Technical Advisory Committee. It's a public event, and it's a great place for presenters to have an opportunity to connect with the quantum industry and also industry organizations to find elite quantum talent entering the workforce. I'm excited. This is our 26th session, and I'm excited to introduce two great presenters today. First, we have Ms. Zixi Li from University of Chicago. She's currently a PhD student from Alex Hai's group at University of Chicago. Her research is focused on using spin defects in diamond membranes for quantum information applications. Our second presenter is Ms. Kaushalya Jhuria. She's a postdoc at Berkeley Lab, working on spin photon qubit synthesis and characterization projects since December 2021. She did her PhD in physics from CNRS Lab in France on the THC spintronics. Again, welcome and looking forward to your talks. Zixi, if you will take over.
Thanks for the introduction and invitation. It's my pleasure to present my work here. My name is Zixi. I'm a graduate student from Professor Alex Hai's group at University of Chicago. Today, I'm going to introduce you a new type of antennas, which are atomic antennas. And specifically, I'm going to emphasize how we make use of germanium weak center as atomic antenna to detect and manipulate the charge environment in diamond. Now let's get started. So first, I want to give a brief introduction to optical antennas. So according to Wikipedia, antenna is defined as a device that can convert free propagating radiation to localized energy and vice versa. To visualize this definition, what I'm showing in the left figure is antenna that is transmitting radiation waves, and the right figure is antenna that is concentrating the energy from a radiation wave to a localized signal. So in this presentation, we will be mainly focused on the second property of antennas. And speaking of antennas, the first impression that comes to our mind is radio antennas, such as our smartphone, TV, Wi-Fi, and signal tower. All of them are communication tools that can transmit and receive signals, and the signal is in radio frequency. So similar to radio antennas, optical antennas are also devices that can convert between radiation waves and local signals. And both optical antennas and radio antennas were designed to resonate at specific wavelengths. And this resonance condition is satisfied when the dimension of the antenna is comparable to its working wavelengths. And for that reason, the radio antenna typically has a size of millimeter to kilometer scale. But for optical antenna, it usually requires a dimension of nanometer scale, and this relies on some nanofabrication technology such as photolithography or e-beam lithography to make such small structures that are comparable to optical wavelengths. And this is why the experimental research on optical antennas were not developed until recent decades. So the most common optical antennas are plasmonic antennas. They were made from materials that can support surface plasmonic resonance, such as metals like gold or silver. Here is a schematic to explain how a plasmonic antenna works. So here is a metallic nanoparticle, a plasmonic antenna that is receiving the instant light. And the light consists of oscillating electric field, and those electric field can induce a dipole inside this antenna, which is a separation of charges. And this will followed by a collective oscillation of free electrons inside this metal. And when the incoming light frequency match the plasmonic oscillation frequency, which is so-called surface plasmonic resonance, it will allow for a strong absorption from the incident light and concentrate its energy to a strong localized near field. And this localized near field can be much stronger than the original incident light, which makes them very useful for enhancing light-matter interaction. To visualize this, we can consider a normal laser beam that is interacting with a single atom. So the interaction efficiency depends on the relative size of the photon and the cross-section of this single atom. A photon typically has a size that is comparable to its wavelength, which is hundreds of nanometer, but the cross-section of a single atom is only about 10 nanometer. So there's one order of magnitude difference, which will make this interaction very inefficient. But now if we consider there's an optical antenna which can control and concentrate the light at nanoscale, the interaction will be strongly enhanced. And because of that, optical antennas were used in many applications. For example, people have been using gold optical antenna to enhance the sensing of hydrogen concentration on palladium nanoparticle. People have also been using metallic tape as optical antenna to enhance the incoming laser and do scanning probe microscopy. And this imaging technique can also overcome the diffraction limit. So I just give some background information about the conventional plasmonic antennas. They are very good antennas for sure. They can strongly enhance the light-matter interaction and have many applications, but they also exhibit some drawbacks. For example, because of the resistance in the material, a plasmonic antenna usually has ohmic loss. So a certain portion of the energy will be converted into heat instead of being entirely stored as electromagnetic energy. So the near field enhancement from plasmonic antenna is typically limited to 4 orders of magnitude. And besides that, to fabricate such a plasmonic antenna, we need to have a very precise control over the shape and the size of the nanoparticle. And this will cause some difficulties in nanofabrication. And additionally, the laser power that is required to activate such a plasmonic antenna is usually on the level of tens of microwatt to hundreds of microwatt. And this will induce a lot of optical background noise. And in this new work that we published 1 month ago, we investigated a new type of antenna, which is called atomic antenna. And the principle of atomic antenna is very similar to plasmonic antenna. So the electron inside this, the electron of an atomic dipole will oscillate when it transitions between a ground state and optically excited state and concentrate a huge amount of energy. And this will make those atomic dipoles excellent antennas. And since it's just single atoms, it does not have ohmic loss. So in principle, it's loss-free and it should have a very huge near-field enhancement. Also, it doesn't require complicated nanofabrication technology. And the laser power that is required to activate an atomic dipole is only a few nanowatts. This will induce much less optical background noise. So in this specific work, the atomic antenna we were investigating is germanium Zixi center in Diamond. So now I want to give a brief introduction on group 4 color centers in Diamond, including germanium Zixi center. So a group 4 color center consists of a group 4 atom sitting in the center of 2 neighboring carbon vacancies. And this group 4 atom could be silicon, germanium, tin, or lead. If we take a closer look at this molecular structure, we can see that these group 4 color centers have so-called inversion symmetry, which means that if we invert the position, the electron wave function will stay the same. And because of this inversion symmetry, those group 4 color centers do not have permanent dipole, which makes them very robust against electromagnetic noise. So they can be put very close to the diamond surface while still maintain very good optical coherence. And besides that, it has a very high fraction of emission into the zero phonon line, the direct photon transition without coupling with phonons. And the right figure shows the electronic structure of silicon Zixi center. It has 2 ground states and 2 excited states. Both of them were split by spin optical coupling. So other type of group 4 color centers will have a similar electronic structure, but with different spin optical coupling strengths. So for SIV, this ground state splitting is 46 gigahertz, but for GeV, this number is 160 gigahertz. So from the electronic structure, we know that the GeV should have 4 zero phonon lines as shown in this PL spectrum. And we are particularly interested in the C line, the transition between the lower ground state and lower excited state. We are interested in this transition simply because it has the highest population. And if we want to take a closer look at this line width, we can take a PLE scan. And we do this by scanning a resonant laser across the C transition frequency and collect the photons that are emitted into the phonon sideband. For most of the time, we will observe a single narrow line that is stable on the time scale of hours. As I discussed before, an ideal atomic antenna should have loss-free transition. In other words, it should have very good optical coherence. It should have a well-defined long temporal profile. And if we translate that into the language of frequency domain, it means that a good optical antenna or a good atomic optical antenna should have very narrow optical line width. So in our specific case, we took the PLE scan at 4 Kelvin, and the line width we got for GeV is 70 megahertz, and this number is very close to the transform limited value. So in other words, the GeV is a very good candidate for atomic antenna. Then we collaborate with Professor Derek Chang to study the near field enhancement from GeV antenna. So GeV in principle is an atomic dipole, and under resonant excitation, any atomic dipole can function as an antenna and generate a near field. And this the intensity of this near field can be expressed using this formula. It's proportional to R2 minus 6. R is the distance to the antenna. In this specific case, it's the distance to the GeV. And gamma naught is the elastic emission rate. Gamma prime is the inelastic decay rate. And in our case, we can consider this gamma naught as transform limited line width, and this gamma prime as non-radiative rate and phonon scattering rate. So from the calculation, we can see that at the distance of 1 nanometer to 4 nanometer away from the GeV, the near field enhancement can reach 5 to 8 orders of magnitude. We also compare the performance of GeV antenna with other plasmonic antennas, such as silver nanosphere. And we found that at small distances, those GeV antenna can outperform the plasmonic antenna. We also noticed that as the temperature increase, the performance of GeV antenna will decay. This also makes sense because the increase of temperature will also increase the interaction with phonons. Now we need to experimentally study the antenna effect from the GeV. So if we only consider the field enhancement, I would say the GeV is not a very unique antenna system because there should be many other atomic dipoles that can have coherent transitions and can potentially be used as antennas. But in most cases, those atomic dipoles are within a solid state environment. And when it generates a near field, it's experimentally difficult to detect such a near field. So in our work, in this specific work, the GeV is a very unique antenna system to experimentally study the antenna effect, because there are many naturally existed vacancies, like carbon vacancies inside diamond. And we can actually study the near field from GeV by studying the interaction between the GeV and the carbon vacancies. So we collaborate with Professor Jhuria, and we found that the carbon vacancy inside diamond can have neutral charge state and negatively charged state. And the charge state switching of this carbon vacancy can induce a stark shift to the GeV's ZPL. And according to their DFT calculation, a vacancy that is 2 to 3 nanometer away from the GeV can induce a second order stark shift of 2 gigahertz. So in most cases, we observe when we took PLE spectrum, we observe that the GeV has a single narrow peak. But in some cases, we observe some GeVs that can exhibit a ZPL splitting magnitude of hundreds of megahertz to a few gigahertz, and the spectral hopping between these two distinct energies. And this means that the GeV has a local carbon vacancy in the proximity. And we also found that we can actually make use of the GeV to manipulate the charge switching of the local vacancy. So the left figure is just normal PLE scan. We scan the laser back and forth across the resonance frequency. So the two hopping states will show up alternately. And in the end, there will be 2 peaks in the average PLE spectrum. We can also park the laser on resonance with peak 1 and pump it for 5 seconds, followed by a 5-second probe scan. And we repeat this laser sequence for 150 times. And in the end, we only see peak 2 in the average PLE spectrum. And this means that the peak 1 never shows up. And vice versa, we will only see peak 1 if we repeat pumping the peak 2. And this experiment indicates that the resonant excitation of a GeV can actually provide a local energy source to charge and discharge the nearby carbon vacancy. So in other words, the GeV is functioning as an antenna to control the charge state of this nearby vacancy. So to summarize, as I discussed, the near field generated by GeV can cause a charge cycling of this nearby vacancy. And this nearby vacancy, the charge cycling of this nearby vacancy can actually have a back action on the GeV itself, which is inducing a stark shift to the GeV's ZPL. In other words, the GeV can also be used as a sensor to sense its own antenna effect. And we can study this near field enhancement by observing the GeV's PLE spectrum, the ZPL. So now we can make use of this property to experimentally quantify the near field enhancement from GeV antenna. The left figure is just time-dependent PLE spectrum of a hopping GeV. As we can see, we increase the laser power from 2 nanowatt to 8 nanowatts, and we see no change on the hopping speed. But as we keep increasing the laser power to about 50 nanowatts, the hopping speed has changed. And this indicates a threshold power to drive the charge cycling of carbon vacancies. It means that the instant laser must arrive this threshold power so that the near field generated by the GeV is enough to drive the charge cycling of carbon vacancy. And the right figure shows a correlation between this threshold laser power and GeV CPR splitting magnitude. And this makes sense because this CPR magnitude, splitting magnitude, simply indicates the distance between the vacancy and the GeV. A larger GPR splitting magnitude simply means that the vacancy is closer to the GeV, so that lower power is required to drive such charge cycling. Then we can compare this threshold laser power of resonant pump with off-resonant pump. And for the off-resonant pump, we use a laser of 633 nanometer. And this is a wavelength that is detuned from GeV's resonance frequency so that it cannot directly activate the GeV antenna. So what this off-resonant laser is doing is that it's directly manipulating the charge cycling of this carbon vacancy. And the laser sequence and the setup is detailed here. And from the lower left figure, we can see that for the resonant pump, a few nanowatts is required for driving this charge cycling, but for off-resonant pump, tens of microwatt is required. And here I want to emphasize that the off-resonant pump require both 1,000 times larger pumping power and 1,000 times longer illumination duration to achieve the same driving efficiency as resonant pump. And that's why we use threshold fluence, which is defined as the threshold power times the illumination duration to compare the resonant pump and off-resonant pump. And finally, we extracted a number of 1 million for GeV with 12 gigahertz GPR splitting magnitude. This means that at a distance of 1 nanometer away from the GeV, the near field enhancement can reach 1 million. So finally, I want to briefly mention the one potential application of this atomic antenna, which is called antenna-enhanced Raman spectroscopy. So currently there are two common methods to enhance Raman signal. The first is called surface-enhanced Raman spectroscopy, where people put a lot of gold nanoparticles beneath the material that they're going to measure. And those gold nanoparticles are functioning as optical antennas to enhance the Raman signal. And this method has some drawbacks. For example, the power that is required to activate those nanoparticles are tens of microwatts, and it will induce a lot of optical background. Also, it's very difficult to fabricate all the nanoparticles to be exactly the same, so the signal is not very uniform. Also, it suffers from ohmic loss. And the second method is called tip-enhanced Raman spectroscopy. And this method also suffers from tip degradation. It also requires transparent substrate, and it's also affected by the background from contamination of the tip. So here we propose a new method for enhancing the Raman signal, which is called atomic antenna enhanced Raman spectroscopy. So if we have a 2D material, we can put it on top of a bulk diamond and use shallow GeV to enhance the Raman signal. And if we have a bulk material, we can also put a diamond membrane on top. So this method has a lot of advantages. For example, since it's just single atoms, there's little degradation and it's very reproducible. And the power that is required to activate GeV antenna is nanowatt level. So it will have much less optical background noise. Also, diamond is a material that is compatible for many biomolecules. And there are also some challenges for sure. For example, if we want to do a Raman mapping, we need a very high density of GeVs. This can potentially damage the diamond lattice and cause some decoherence. So finally, I want to thank my team, especially my research advisor, Professor Alex Hai, for coming up with this smart project and building all the connections between our group and other groups. I also need to thank my mentor, Xing Han, who gave me a lot of guidance during my PhD journey. And I know for the stark shift calculation and Gali group for the DFT simulation, Chang group for the near field enhancement calculation, and Ashram group and Argon for providing the diamond materials. Yeah, thanks for listening. I'm happy to answer any questions.
Thank you, Zixi. I have a question. Besides germanium vacancy centers, are there any other quantum systems that can be used as atomic antennas?
Yeah, that's a great question. So if we take a look at this formula, this near field enhancement really depends on the ratio between this gamma prime and gamma naught, which means that we need to have very coherent optical transition, and this condition can be satisfied by many quantum systems. So besides good for color centers such as germanium weak center, there are also a lot of other systems such as this rare earth dopants, defects in HBN, defects in silicon carbide, and a lot of molecular qubits.
Excellent. Was this is this room temperature or it has to be cryogenic?
So in this specific work, we perform all the PLE scan and all the measurement at 4 Kelvin is cryogenic temperature. But this also inspire us to search for other atomic antennas that have better performance at room temperature than GeV. Because from our calculation, as the temperature increase, there's a huge decay on the performance of GeV antenna.
Excellent. Okay.
Yeah.
Very good. Are there any other questions for Zixi?
I have one.
Yes.
Is that allowed?
Yeah.
Excellent.
Sure.
So I am not a STEM person. Let's put it that way, right? My knowledge of science is very minimal. What practical applications could you see your research having, right? If you had to assign a use case to this kind of research, where would you see that?
So for my presentation, I only gave a simple example, which is the Raman spectroscopy, and this type of spectroscopy can be used for many applications. And besides that,
but what applications? Remember, just pretend that I am a 2-year-old.
So besides spectroscopy, I would say, well, maybe for community.
No, what is Raman spectroscopy? What is that?
What applications is that?
What use is it?
I see. So when you shine a light onto a material, it's gonna scatter the light. And most of the scattered light will stay at the same energy as your incident light. But there's also like less than 1% of the light have a different energy, which we call Raman scattering. And this signal can tell us many information about the material, like how this molecular structure looks like, and what does this lattice looks like.
So diagnostics and material sciences.
Yeah. Exactly.
Okay. So what other uses are there?
So in this specific work, we also propose a called Fred spectroscopy. This is basically we can use this type of atomic antenna to find the signal that is very weak and it's very difficult for other measurement method to detect. Yeah.
What does that do? For instance, like again, are you talking about in terms of capturing, I don't know, alien transmissions from way out there? Is this a possible way to identify if they're trying to communicate with us? Because even if it's super weak, you could see it. Is it like
that's a great question. I won't say it's not possible. I would say it's possible. It's because it's antenna, it can enhance any signals that's in the optical wavelengths, I would say it's possible. Yeah.
Okay. Okay. Excellent. Thank you so much for humoring me.
Thank
Thank
you.
you.
Thanks for the questions. Thanks, Zixi, again.
Mhm.
Kaushalya, you can.
Sure, I can start my screen. So, hello everyone. I first of all like to thank the organizer, Lisa. I'm sure I'm not pronouncing correctly, but thank you so much for the invitation. And I'm more than happy to present our recent work, which is related to programming the formation of quantum emitters in silicon for quantum information science related applications. So here is the brief outline of my presentation. So I'll first walk you through the introduction and motivation about the work I'm going to present. And then I'll introduce you to the color centers as potential qubit candidates for quantum applications. And I'll briefly walk you also through the synthesis and characterization methods for color centers. And finally, the results where we have recently managed to program the formation of different color centers that could be potentially used as qubits for quantum applications coming from silicon as the host material. And finally, the conclusion and perspective. So when it comes to the motivation, we all are sort of aware about the Moore's law, which says that every 2 years, the number of transistors you can put in your chip or the CMOS chip will increase by an order of magnitude up to. So we have been seeing this trend. The Moore's law is working really well, but just until recently, and now we are kind of reaching to a saturation point because of different issues. For example, the heat management. So we are keep on miniaturizing our devices with time, and that was basically increasing the functionality and also increasing the number of transistors that we could put in the same scale of chip. So now the idea is also like if we keep on increasing, there's a limit, because at some point you will reach the electron mean free path of your electron, and then you basically cannot just use the electron's charge degree of freedom and move it and make all your devices out of it. So you need to basically go through a paradigm shift if you want to keep moving ahead and keep increasing the functionality of your devices. So basically for classical computing, we are using the CMOS platforms, and the fundamental unit in all these CMOS devices is basically a transistor. And then just by how we are connecting them, and we basically do all our calculations, classical calculations. Now with the quantum, which is basically just an analog to the classical bit, we would like to perform similar kind of operations, but the idea is to use the quantum mechanics concepts to do the calculation. Essentially meaning that we need to find an analogous to the transistor now in the quantum world in order to process, sense, communicate, and compute the information using the principles of superposition and entanglement. And the reason why we would like to do that is because they provide enormous basically functionalities. For example, if you compare the classical bit versus the quantum bit, so if you scale up your classical bit, so if you have n number of transistors and you increase them by, let's say, twice, your capacity increases by twice. The same if you do with the quantum bit, the capacity increases by 2 raised to the power n. Because in this case, what we essentially have is not just a simple two-state system providing zeros and ones, but you can have 0, 1, and anything in between 0 and 1 because you have a quantum mechanical system which follows the superposition principle. So you can have n number of states within 0 and 1. For the classical case, we use Boolean logic, so and or NOT gates. Analogous to that in the quantum world, we use C-NOT gates. And then, as I mentioned already, like in the classical case, we only have zeros and ones, so 2 states. Whereas in the quantum world, we can have zeros, ones, and anything in between. So just as a part of motivation, in late 2019, Google claimed that they managed to solve a problem that would take 10,000 years for the world's fastest supercomputer based on the classical computing scheme. And they managed to do it just in 200 seconds using the quantum computer they have, which is based on a particular type of qubit approach where they use superconducting materials. So now for introduction to qubits, as I already mentioned, these are nothing but the quantum analog of the classical bit. And essentially to make a qubit, you need to fulfill 2 to 3 different requisites. So it has to be a quantum mechanical system. It needs to follow the principle of superposition, and we should be able to perform entanglement experiments on the system. And then it should have, when you measure it, it should have a distinguished 2-level state. So if you qualify, if any candidate qualify these prerequisites, we should be essentially be able to use it as a qubit. And because of that, we have actually n number of ways to make a qubit. You might have heard more about the superconductors, where we make Josephson junctions with a superconducting material and then perform the qubit operations on it. This is one of the most mature qubit approach and one of the first. And then we have other leading qubit candidates, for example, ion traps. So essentially we do the same, but with ions. Then you have quantum dots, and basically then there's another approach called color centers. And in the last presentation, we went through a particular type of color center for slightly different kind of applications, but the idea is still the same. It's essentially color center, and because it basically fulfills those 3 requisites to be a qubit candidate, we can use it. And then there are actually so many other candidates also that are potentially can be used as qubit candidates. Here in the bottom left, this is basically a comparison table between different qubit technologies and the best and the worst argument about their applications for qubit. So then basically, just to summarize, essentially what we are ending up in terms of like if we compare all these technologies and then try to conclude, what we are lacking is basically scalability. So some of them do provide that you can scale them up in terms of fabrication, but scalability is not just the fabrication, it's also about if you can make n number of qubits, can you actually use them and leverage the capacity that they could provide? Then how well you can control them. So you should be able to manipulate their quantum states with external stimuli, making sure that some random noise is not basically, changing the quantum state. And it's just when you really want to manipulate the quantum state, it's happening. Then you should have a long spin coherence time, basically meaning when you are trying to perform some calculations or operation on your quantum computer or with your qubits, they should not lose their quantum state during the operation. Otherwise, it will not make sense in terms of the result what we measure. So the spin coherence time to be longer than what your computation time you want to have. Then it should be easy to integrate them with photonics and electronics. to basically realize your qubits at large scale and eventually make quantum networks and quantum computers at large scale. Now, when it comes to color centers, these are basically atomic level point defects in crystal lattice. So you take any lattice, you will have some sort of defect in it. Even if you take the most pure material we have, which is silicon, you still will end up having a couple of defects in it. Until few decades, people were actually wanted to get rid of the defects because they were essentially destroying the overall bulk property of that material. But recently, it turned out that if we can manipulate these point defects or also called the color centers, you can actually use them as qubits. So just for an example, if you take a diamond material, you can have a bunch of color centers in it. For example, NV center is among the most popular one, where you replace two carbon atoms and replace them with nitrogen in one place and keep vacancy in the other place. So this is like nitrogen vacancy, so NV center. And this kind of point defect also has basically a spin to it due to the free electron it has in its structure. And then you can basically use this NV center for quantum applications because it basically fulfills the three requisites. It's quantum mechanical in nature. You can perform the principle of superposition and do entanglement with it. Now, similar to that, there are other material platforms that you can use to basically have your point defects and color centers in them. And in the right, you're seeing a comparison slide for different color centers coming from different host materials. And then on x-axis, it's the emission wavelength. So if you look at diamond or silicon carbide, you see that most of the color centers in these materials, they are emitting light outside the telecommunication band. So telecommunication band is actually something we desire to have our emission in because that's where the optical fiber losses are the least. So if you want to have a long distance communication and send your signal from one point to another point, and the signal is in the telecom band, then you will have least losses, and that's why it is desirable to have. Now the idea is what colors and what other material platforms that we could maybe explore and which might have the color center emission in the telecom band. And one desired material could be silicon, because silicon, as we know, is among the most pure material we have. Scalability due to its CMOS compatibility is not a question. We have been using silicon for a couple of decades now, so we know the most about this material. And luckily, we already have a bunch of color centers in silicon emitting light in the telecommunication band. And inherently, the spin coherence time in silicon is also good. There can be a comparison also. It's not the best one, but it's still good enough to perform the fast operations that we would like to do. Now here on top, these are basically different color centers that you can have in silicon. For example, the W center forms when you kick out basically 3 silicon atoms from their lattice positions. So now they are sitting at interstitial sites in the lattice. And if you have 3 of these silicon atoms in the near vicinity to one another, they actually form this color center called a W center. And if you excite them with some laser, you can actually have the emission at about 1270 nanometers. You can have a G center when you basically introduce 2 carbon atoms at the substitutional site inside your silicon lattice, connected to a single silicon interstitial. And if you have these 3 atom pair, you can have a G center, which emitters light at 1278 nanometers. And similarly, you can have a CI center, and a T center. And it's basically how the structure looks like. And then they basically give different properties. So for example, if you look at the T center, the T center, in its structure, it has 2 carbon atoms, 1 hydrogen, and a free electron. Now, what you can directly do is just manipulate the spin state of your free electron, and you can realize a spin photon qubit out of it. And similarly, in the CI center also, there is a free electron connected to the carbon, and you can manipulate the spin degree of freedom here, and you can have a spin photon qubit. So not all these color centers do have a spin degree of freedom, and but what they can provide at least is a single photon source, which is also a one way of realizing qubits. But in case of some of these color centers, you can also have a spin associated to the single photon. So then you have a spin photon qubit, not just a single photon emission. And then you can basically have this spin degree of freedom, and which basically helps you directly use it as a spin photon interface. Now, where are we in this whole approach? Is basically, it's easy to make some color centers, but it is challenging to make them reliably with high quality at desired locations. And this is where we are at this moment. And when I say high quality, there are different things that we need to keep in mind. For example, where the emission is. So it is desired to have it in the telecom band. What is the intensity? So in terms of sensitivity, we need to have intense enough signal so that we can sense it. And then the line width should be narrow, which is also related to then the lifetimes. And then the spin coherence time, as I already mentioned, it should be long enough that you do not go through decoherence process while you're performing the operation. So now when it comes to how do we form these color centers, there are actually a bunch of different ways. For example, the most commonly used way is when you do some ion implantation to introduce the foreign elements in your lattice, and then do some thermal annealing process. You can also do direct proton irradiation or electron beam irradiation, and realize some kind of some color centers in silicon. And it's actually also not just limited to silicon. It goes well with other color centers in other materials as well. And then you can also do ion beams or plasmas or lasers to do that. Until 2020, we were actually whatever emission we were getting was basically coming from a cluster of these color centers inside silicon. So that's why it was difficult to use them directly as qubits. But in 2020, for the first time, it was reported that you can actually make them at single center level, meaning you can isolate this color center or this point defects, and hence have a single photon as an emission. And then if you play around with different recipes, for example, if you change the annealing parameters, like the annealing time and the temperature, you can basically tune some like properties. For example, you can tune the density. So there's a nice window for your annealing time where you get single centers in the silicon. And if you are outside that window, then you have more chances to have the cluster of these defects. So you can do some fine tuning with these parameters. And then when it comes to how do we characterize them, it's basically using photoluminescence. So you essentially excite your defects or the color centers, and then you basically sense the reflected signal that is coming out of your sample. And then depending on what color centers you form. You will basically, if you use the spectrometer, you will see the signal as a function of wavelength. And with some modification in your setup, you can have time resolution as well. So you can basically not only just take a single static like a spectrum, but you can also know like lifetimes. So how the emission is changing as a function of time, and also other properties like the spin coherence times, etc., that you can do with photoluminescence. Now coming back to the main issue that we have been trying to solve is basically how to make these color centers at desired locations with high quality. So if you compare with what people have been doing by far, when they do ion implantation and rapid thermal annealing, you basically end up having these color centers randomly located in your lattice. So they are not at local sites or wherever you want them. So we need to basically come up with a new approach by which we can decide where do we need these color center. Also, when you use different approaches, what we have been seeing is that you normally make the G center, which is among the most commonly formed color center in the silicon. So you do any sort of irradiation, be it just ion implantation or electron or proton irradiation, you end up getting the G center. And that is also one reason why we cannot easily make other color centers, because we are flooded with the G center. Now, what we have recently done is modified the conventional approach, and then also including femtosecond lasers in the picture to locally manipulate the formation of these color centers. So what we essentially do is we start with a silicon on insulator wafer, so which is essentially a silicon bulk wafer, and then few micrometer of silicon dioxide and another few 100 nanometers of silicon on top. And the reason why we would like to have this kind of SOI wafer instead of just a silicon wafer is because eventually we would like to have a integrate our qubits with other photonic components like photonic crystals, waveguides, etc., to realize a full-scale quantum computer. So it's important to basically study all this or make all these qubits on silicon on insulator devices so that we can directly switch from one single qubit level to a full-scale quantum network. So what we essentially do is first start with this wafer, then do carbon ion implantation to introduce carbon in the wafer, and then do thermal annealing process, so which people have been doing. What we have done differently is basically during the thermal annealing process, we have changed the annealing ambience first. So people have been using inert gases like nitrogen or argon. But what we have done is used forming gas, which is in our case, it's 10% hydrogen and 90% nitrogen. So essentially introducing hydrogen in the lattice during the annealing process. And what it does basically is, maybe I'll first come here. So what it basically does is it passivates the most commonly formed G centers. So when you have ion implantation and thermal annealing in inert gas ambience, you end up making the G center, which is a pair of two carbon atoms and a silicon atom. And now if you introduce hydrogen in its vicinity, what happens is the transition dipole moment of this color center, which is in experimental terms, is the intensity, basically drops by about 5 orders of magnitude. So you basically passivate this G center by introducing hydrogen in the lattice. And by doing that, you also form a new type of color center, which is a CI center. So you have a carbon in your lattice because you introduce it with the ion implantation, and now you have a hydrogen. And when you have this hydrogen close to CI center, the intensity that you measure experimentally increases by a couple of orders of magnitude. So by just making this small change of replacing inert gas with hydrogen based forming gas, you basically can passivate this commonly formed G center while making a more interesting CI center, because the CI center not only can provide you a single photon, but also has a spin degree of freedom to it. So it is basically a spin photon qubit. So when we do this process, we can have the CI centers. And now we wanted to basically, so at this stage, everything is still located at random places. So the color centers we are making are randomly oriented in neolattice. Now what we would like to do is manipulate them locally so that we can erase from the places we don't want them and keep them or write them with desired properties where we really want them. And to do that, we wanted to have femtosecond laser pulses. So just as a proof of concept, we started out with just age received SOI. We didn't do any ion implantation in this case. This SOI was basically from storage. So we have been we had this wafer for 10 years in our lab, and we first checked how much carbon, hydrogen, and oxygen, these hydrocarbons, are there in the wafer just from the storage. And basically in the center, what you are seeing is SIMS, which is secondary ion mass spectroscopy measurement, and which essentially tells you as a function of depth what is the concentration of your different elements you have in the lattice. So you can see that already, like for oxygen, hydrogen, and carbon, there's enough of these elements present, which essentially tell us that you should be able to make some of the color centers already in this wafer, and you don't need to essentially introduce additional carbon or any other element with ion implantation. So then we started out with this wafer and irradiated it with femtosecond lasers of different pulse energies. And in the top right is basically the PL photoluminescence raster scan showing the different color centers formed by femtosecond irradiation of different pulse energies. And then if you zoom in on one of these spots, you have the spectrum, which is, for this case, it was related to the G center. And now if you change the laser intensities, you can actually fine tune the different properties. For example, you can change the density of the G center, you can change the line width and the lifetimes. So at this was basically a good proof of concept to check if femtosecond laser can make any color centers at all. And then once we knew it, we wanted to now switch to the more promising color center, which is the CI center. And as I already mentioned, we formed it by replacing the inert gas with forming gas. And now we have the CI center. At first, we used the parameters such that the emission is coming from cluster of these CI centers. So we are not having isolated centers. We have cluster of these centers. And then we basically came with femtosecond lasers of different pulse energies at different locations. And then what we realize is this. So the black spectra corresponds to the emission coming from cluster of these CI centers, while there was no G center, as you can see. And the CI center is at around 1450 nanometers. Now, if you come with femtosecond laser, you basically slightly modify your CI center here and also start making the G center, which is not controversial. As I already mentioned, you can make it even with a bare SOI wafer. Now, if you keep on increasing the laser energy per pulse, at some point you can completely passivate the CI center while partially passivating the G center. And if you keep moving further in laser energies, you can bring the CI center back. So basically, you can locally modify or program the formation of these different color centers just by changing the laser energies per pulse. And also by introducing the hydrogen in the picture, you can do it do it for different color centers. For example, what we have seen also is that by changing different annealing time and the temperature profiles, you can make even more like different color centers, not just the G and the CL, but others as well. Then this is the final measurement that we do in order to basically double check if we can if we have the emission from a single center. So if we keep on fine tuning the laser energies at for a very small parameter range window, we can actually make these C and the GI centers at single photon level or isolate them basically. And these are basically just the optical measurements to prove that the emission we are seeing is indeed coming from a single photon source. So the ultimate proof is being done by Henry Brown interferometer. And when the signal basically goes below 0.5, which is a second order autocorrelation function. So if it goes below 0.5, we say that it is coming from a single photon source. So I think I'm already over the time, so I will be quick here and summarize. So what I have basically presented today is first introducing you to the color centers in silicon as potential qubit candidates. And now we can program their formation by modifying the conventional approach and bringing the femtosecond laser into picture. And these silicon color centers are promising spin photon interfaces for large-scale qubit integration. And in doing so, the role of hydrogen was crucial. So yeah, thank you.
Excellent. Thank you so much. Great presentation. So I have a question. How is this qubit scheme better than the others? And then the second part is that next steps to realize full-scale quantum network. How do we go about that?
Thank you so much for your really nice question. So in comparison, one strong point is we have spin photon as the output, or essentially we get the photon as an output with the spin information encoded into it, because we have spin in the structure of our defects. And because they are in the telecom band, we can have long distance communication. So if you compare it with superconducting qubits, etc., then you have everything more electrically, and then you at some point need to change it to convert it to photons, and then the conversion take place. And then also if you want to go in the telecom band, then that brings another challenge. So we already have our qubit in the telecom band. That's one of the biggest things. The other thing is everything is happening with silicon. And this is definitely a material of choice, because we already know a lot more about silicon than any other material. So we can scale things up, and now to realize a large scale quantum network, it's basically now a question of connecting these qubits. So one qubit to rest of the qubits in the system now. And what we have done is basically one major step, but still at the fundamental level to actually make them reliably. It's important, but it is not all of it. Now we need to connect these qubits with one another and realize entanglement first, maybe at short distance, then at long distance, and then not just entanglement between two qubits, but multiple of these qubits. But just because it is telecom band, it is silicon, and we already know a lot about silicon, these steps will be reasonably, like it will be doable. And yeah, that's basically the main point about this approach, why
Okay.
it is exciting.
Excellent. No, it's very exciting. So I have one more question, I guess that
Sure.
was posted. It says, how does this advance the potential in applied quantum capabilities? From what I understand, it sounds like it has applications for adjusting to a more useful and customizable qubit. So yeah, so I guess the answer would be that how is it advance the potential, the applied quantum capabilities would be for long distance quantum networking, correct?
Yeah,
Okay.
definitely.
Yeah, because the qubits, because you mentioned qubits, I assume the question says, is that going to be used for quantum computing or more for quantum networking?
So actually, the nice thing also about the silicon spin photon qubits is that you can also use them as flying qubits and not just the stationary qubits. So if you talk about superconducting Josephson junction devices, you will always have them in one place. They are static qubits. So they can be used nicely as logical qubits, but not as flying qubits that you also need as interconnects for the long distance communication. And here you can use them both as logic qubits and as flying qubits. So if you make a quantum network with these color centers, you actually are making a quantum computer with them. And it's not just like,
It'll be a
yeah,
distributed quantum computer. Yes,
yeah.
exactly. Very good.
Mhm.
Excellent. Any other questions?
Hi, my name is Wendy Wu. I have a question about the quantum dots. Because I've seen a lot of people leverage the quantum dots for medical devices.
Right.
What is that for?
So actually, I have to agree that I don't know a lot about quantum dots. The only thing I can mention here is that when we try to use quantum dots for, let's say, the quantum computing application directly, the main issue is about the connections. So you need for each quantum dot so many different electrical connections, and the number of connections you need to use a single quantum dot is actually one of the limiting factor when you want to scale it up and basically have a bunch of quantum dots. So that's one thing, but I think for the medical application, it's definitely very, very promising. And I don't know a lot about it. I have just heard a few things about it that you can maybe I should not speak so much about it. Like you can attach them with the enzymes, and then that also leads to so many new biological applications. So definitely maybe for other applications, it can be a great candidate. But for quantum computing, I would say there's a limitation associated to quantum dots.
Yeah, because of the connectivity, right? You mentioned the charts.
Yeah.
Thank you. Thank you so much. That's all I have. Thanks.
Thank you.
Thank you, Wendy, for the question.
I also have a very short question. So thanks for the excellent talk. It's very cool that you show that by this laser writing method, you can accurately control the position of your color center. I'm just curious, how's the spin coherence of these color centers you created, and how homogeneous, how uniform between color centers to color center?
Yeah, thank you so much for a really nice question. So, one thing is about the spin coherence time. What we know by far is actually about the T center in silicon, which is actually the spin photon qubit. So we have the spin coherence times in the range of few microseconds for this one. And then for the CI center, it is new. We still need to do the spin property characterization for it. So I cannot tell you right now, but by seeing the other optical properties, which are also somewhat related to the spin properties, it should be within the same similar range. Other thing we could do always is use isotropically enriched silicon as the platform. So when we do that, you can use the nuclear spin, which we already know that it has spin coherence times of about an hour.
Yeah, sure.
So, yeah.
Yeah,
these
thanks.
are. But we still need to do the spin factorization,
Yeah,
which
sure.
is, I think I have mentioned
Good
in the
luck.
next steps. Thank you.
We're at the end of the presentation. Thanks again, Zixi and Kaushalya, for great presentations. And
you.
just to announce, the next session is going to be on the second Tuesday of September. I believe it's September 10th. Thanks everyone for joining, and have a great day.